put that in. Thank you. Okay, first off, you guys know that that's water, right? H2O. Now, hydrogen has one valence electron, right? And there are two hydrogen atoms in the formula. Yeah. Oxygen has how many valence electrons? 6. So 1, 2, 3, 4, 5, 6. Now, for atoms to be happy, they want to look like noble gases. They want a full outer orbital. So when oxygen meets up with two hydrogens, they are going to share these two electrons. Because if they share these two electrons, and they share these two electrons, now, if we just look at one hydrogen, this hydrogen is happy. It has a full outer orbital, right? Because it only has the one orbital and it only holds 2 electrons. This hydrogen is happy for the exact same reasons, right? And then if we just look what's around oxygen, oxygen is happy because it has 2, 3, 4, 5, 6, 7, 8 valence electrons, so it is happy, right? So by sharing these, and they are represented not by this, but they are represented by a straight line. By sharing those electrons, all 3 of these atoms are happy. However, remember, oxygen is very electronegative, meaning the electrons will spend more time around oxygen, right? They're going to spend more time around oxygen. So water ends up having a positive end. So these lines that I'm drawing are called dipoles. This is the plus, and it always points to the negative end. And if you've done vectors in math, you know that a vector shows you direction and magnitude, and you can sum vectors up. And if they're going opposite directions, they cancel out, right? Well, there are 2 directions here, so they kind of average, and I say that lightly, to a dipole that looks like this. They kind of average to a dipole that looks like this. These dipoles means water is polar. Polar. So when you draw a water molecule in your notes, or you have to represent water molecules, the little balls are your hydrogens and have a positive end. And the big guy is your oxygen. And you can indicate 2 negative regions or just 1, doesn't matter. Doesn't matter, 2 negative regions or just 1. So water is polar. Water is polar, yes? Has everyone written this down? You need to be able to draw water molecules. For this class, for AP exams, water. You need to be able to draw water molecules. Now, opposites attract. Opposites attract. So this end of the water will attract positive charges. Does that make sense to everyone? And this end of water molecules will attract negative charges because opposites attract. Okay, so that's a quick review of water. Now, we've got even more.
Let's add a small amount of table salt, sodium chloride, to water. As you know, sodium chloride dissolves in water. Click on the zoom button to view sodium chloride dissolving in water on a microscopic scale. All the water molecules interact with the positive and negative ions of salt.
Okay, so sodium chloride. Here it shows you sodium is the smaller circle and it's positively charged. Chlorine is the larger circle and it's negatively charged. Remember, chlorine has taken the electron from the sodium. Yeah. This crystal is all happy and it would just sit there, but you've thrown it into water. And water, the different ends of the water, is literally going to force apart these ions because the water is polar. So the water is physically ripping that crystal apart.
The positive ends of the water molecules are attracted to the negative chloride ions. The negative ends of the water molecules are attracted to the positive sodium ion. This interaction between water and the salt ion causes.
See this negative one? See how it's covered with the little white balls? Those little white balls are what? Hydrogen, positively charged hydrogen. All right.
The salt to break apart or dissolve.
See the red, these big red ones pulling this guy? What's the plus? Sodium. Sodium, and the red balls are the oxygen or negative end of the water molecule.
In water.
So right now, several of you have to redraw on your worksheet where you had to draw your ions surrounded by water molecules in the beaker. I want a positive one and a negative one surrounded appropriately by water molecules. So in that beaker on the bottom of the page, you don't have to indicate what ion you are putting in the beaker, but definitely surround it correctly with the water molecules. If I'm asking you to do this here, when else do you think you're going to have to do it?
Is there a test?
Quiz and test, absolutely, more likely a test. Let's see if it says anything else. Yep. Back it up.
Polar water molecules interact with the positive and negative ions of a salt. The positive ends of the water molecules are attracted to the negative chloride ion. The negative ends of the water molecules are attracted to the positive sodium ion. This interaction between water and the salt ion causes a salt to break apart or dissolve in water.
Pretty good. Okay. So back to dissociation problems. When checking, I noticed you had to dissociate dissociate. How do you spell dissociate? Dissociate. Okay. Dissociate. Dissociate ionic compounds. So dissociating ionic compounds, remember this is physical, and this is the table. And I saw, if I'm correct. Was that, did you have to dissociate one of those? Okay. So we know it's ionic. Why? The first element is a metal, right? We know it's ionic. First element is a metal. You picked up your periodic tables and you will soon have memorized that, and this is solid form, so it's a solid crystal. And we're going to put it into water, which means when it splits apart, it will be aqueous. So we're going to be making two aqueous ions. Metals, left-hand side of the periodic table, they lose their electrons to nonmetals. Nonmetals take them. When they lose their electrons, they become positively charged. So we know copper is going to be a positively charged ion. Oxygen is a nonmetal, and we know oxygen will be negatively charged ion because it's nonmetal and it takes electrons. And if you look on your periodic table, it gives you the charge of oxygen. What is it?
-2.
-2. This is pretty much always, unless you're dealing with peroxide or hyperoxygen oxides, which you won't do in here. So knowing that this is -2, you have to then look at how many coppers there are for every oxygen. And there are 2 coppers for every 1 oxygen. So each one of those coppers must be +1. Does that make sense to you guys? And then when you balanced it, you get 2 copper ions and 1 oxide ion. That makes sense to you guys? Okay. So let's just randomly kind of, there's my oxygen, and I'm just gonna make this copper and make this copper. Okay, this is it as a solid. When I break it apart in solution, the copper is not together, but I have 2 of them. And I have 1, there's my oxygen, 1 - 2. Does that make sense? So one thing broke apart into 3 things. Does that make sense to you guys?
Yeah.
One thing broke apart into 3 things. If we started with 10 of these, 10 of these, 10 of these. We're starting with 10 of these. How many copper ions would we have? We'd have 20 copper ions. Does that make sense to you? And how many oxygen ions? 10, for a total of 30 total ions. We start with 10, we get 30 total ions. That makes sense to you guys? Cool. Super cool. Any questions on dissociation? No questions at all. Will you have to do this on a test? Yes, that's why you get to keep your worksheet, right? So you can study and review and be able to dissociate things. Now, you were asked to learn all by yourself how to find empirical and molecular formulas from percent. Where do we get the percent from? You just turned in a bunch of percents. Yes. Yeah, where do we get percent composition from? Nope. I'm sorry. It tells you in the problem, okay, bigger picture. Big zoom out. I get it tells you your percent. You guys just turned in a bunch of percents to me. What am I talking about? And you picked it up graded. Huh?
Maths. Like you get it from the maths.
Nope. Yeah. No. No, 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 no. No, 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 no. What did you guys pick up? Your lab books. And what did you do in your lab book? What did we spend days doing? Baking, separating. Why'd we do that? Yeah, to find percent composition. So you get percent composition in the lab. In the lab. So you have some piece. Chemistry is the study of matter. What do we have to do? We separate the matter. Why do we separate it? To get percent composition. Why do we want percent composition? To get the chemical formula. See how this is stepping? Percent composition to chemical formula. Yeah, okay. So the percents are from the lab. Not necessarily a high school lab, but from a chemist lab. And then there is, what is the difference between empirical and molecular? Empirical is the lowest whole number ratio, right? Lowest whole number ratio. And molecular is any multiple of the empirical. So CH4, I know is an empirical formula because one of the elements, there's only one of them. You can't get lower than that. So if you have a single element in a formula, you know you're at the empirical formula level. All right. So that makes it easy to identify it. What is a molecular formula of this empirical formula? Anyone? Just give me a molecular formula of C2H8. C2H8. Is that the only one? No. Oh, we could just keep going. We could do C20H80, right? C20H80. You could absolutely do that and totally exist. So from your worksheet, is there anyone you guys want me to go over? Did you understand them all? Anyone want me to do one? Anyone want? Number 4. So number 4 is asking, what is the empirical formula? So we're looking for the empirical formula of a molecule that contains 65.5% carbon, 5.5% hydrogen, and 29.0% oxygen. So you're given percentages, and there's a little song that traditionally goes with this. It's called percent to mass, mass to mole, divide by small. Oh, and you got to hold that a long time because you're dividing many things. Oh, and then multiply till whole. And you got to hold that a long time because you're multiplying many things, right? When you're doing this. So to go from percent to mass, you just do it because we are the dominant species on the planet. We can just get rid of that and make it a gram. That's how you go from percent to mass. We're just assuming 100 grams. Percent to mass, then mass to mole. There's the conversion factor that will go from grams to moles, and that is located on the periodic table, right? So 12.01 grams per mole is the molar mass of carbon. My grams are going to cancel, and that will leave me with moles. This one, I'm dividing by 1.01 grams per mole. My grams will cancel and I'll be left with mole. And this one, I'm dividing by 16.00 grams per mole. And my grams cancel. So in my calculator, I've already done 2 of the steps, percent to mass, mass to mole. To get to mole, I'm just going to divide 65.5 divided by 12.01, and I get 5.45. 5.45, and that's mole of carbon. Now I'm gonna do the next one here. 5.5 divided by 1.01, and I get 5.45. 5.45, and that's mole of hydrogen. And then my last one, I will do 29 divided by 16. And I get 1.81. 1.81. Yep, mole of oxygen. So what is the third step? Divide by small. Which is the smallest one?
Oxygen.
Yep. So we're going to divide this by 1.81. You have to divide all of them by the smallest. 5.45 divided by 1.81, and I get 3, 3, 1. 3, 3, 1. 3, 3, 1. So what does that tell me? That tells me the empirical formula for this molecule is C3H3O. There's 1 oxygen, 3 hydrogen, and 3 carbons. Then the second part, so this is part A, that is the empirical formula. The second part says if the molar mass for the compound is 110 grams, what's its molecular formula? So the first thing you want to do is find out what this weighs. So 3 times 12.01 and 3 times 1.01 and 1 times 16.00 plus 3.03 plus 16, and I get 55.06, and that is grams per mole. And that's of the empirical. That's of the empirical formula. So this guy has that molar mass. And it's asking, well, what if the molar mass is 110.00 grams per mole? You guys know already? How did you... What'd you do? Yeah.
Took the percent of 120. So if it was 20%, you take 10% of 1.
Yeah. So 55 goes in there 2 times, right? 55 goes into 110 2 times. So that means the molecular formula must be C6H3, oh, H6O2. We're multiplying this guy by 2 to get that guy. Yes,
You were asking a question like this on the test, but we'd still get credit if we maybe kind of reworked every single question with the new molar mass at the end, because that's just like a total hypothetical thing. I totally didn't do it on the worksheet.
what?
I didn't realize that you could just multiply it, and I did it the way that the example video had it, so I reworked every single question. And I'm wondering if we were to do one of those connected problems on a test, we'd still get full credit if we reworked it.
Yeah. Which way do you like better?
That one's definitely a lot easier and probably a bit more fun than sitting there in my kitchen table for an extra 15 minutes.
What did you do?
You know, like there were a couple connected ones where you figure it out and then they give you a new, well, like total molar mass.
Uh-huh.
I reworked every problem with the new molar mass, I found the percentage, and then I divided it by the molar mass again.
Okay, so. Okay, so you're just going to go molecular divided by empirical. And that will give you the multiple. Right, so if you take the molecular's molar mass, a big curvy M stands for molar mass, guys. And you divide it by the empirical's molar mass, a big curvy M stands for molar mass. And then you'll get the multiple to use for multiple to use to convert your empirical to your molecular. It's a little easier than trying multiple ones. Oh, I'm sorry. I'm super sorry. So today we got something new to cover. Any other questions on this or any other problems you'd like me to do? Do we feel comfortable doing this? I'm sorry, yes. Can I do 5? Yes, I can do 5. Okay, so empirical and molecular formulas, they come from percentages. It tells you that a 50.51 gram sample of a compound. So I'm just going to draw, we got a pile of a compound here. We put it on the balance and it weighs 50.51 grams. And they tell us it is made of 2 things, phosphorus and chlorine. They tell us it's made of 2 things, phosphorus and chlorine. Then they break it apart and they say we get 11.39 grams of phosphorus. Now it's made of phosphorus and what? Chlorine. If we know what we started with, and we know that this is phosphorus, do we know how much chlorine there is? Yeah, because matter is not created or destroyed. So we just do 50.51 minus 11.39, and we get 39.12 grams of chlorine. I should put the CL over here. Grams of chlorine. So again, that hasn't helped us because to find the empirical formula, what's the first step? Percent to mass. So given this information, can I convert it to percentages? Yeah. Everyone comfortable converting this to percentages? So the percent phosphorus is 11 point the part divided by the whole times 100. So 11.39 divided by 50.51. And that gives me 22.55. 22.55, and that's percent phosphorus. And if I do 39.12 grams over 50.51 grams. That's the chlorine part over the whole times 100. 9.12 divided by 50.51, and I get 77.45% chlorine. Now I can start the song, right? Percent to mass. Well, 22.55 grams of phosphorus and 77.45 grams of chlorine. Then I need to go mass to mole. To go from mass to mole, I divide by the molar mass. Chlorine is 35.45 grams per mole. My grams cancel. So I'm converting to mole. Phosphorus is 30.97 grams per mole. My grams cancel. So 22.55 divided by 30.97, and I get 0.7281 mole of phosphorus. And 77.45 divided by 35.45, and I get 2.185 mole of chlorine. What is my next step? Divide by small. Divide by small. This is the smallest. 0.7281 and 0.7281. So this becomes 1 and 2.185 divided by 0.7281 equals 3. So what is the formula for our unknown compound? There's 1 phosphorus for every 3 chlorines. Yes.
Is there one you have to put it in?
What?
Is there one specific order you have to put it in?
Yes, there is a specific order you have to put it in.
How do you know?
So you want to traditionally put your positive charged, least electronegative atom first, right? So least electronegative, this guy first. It's also positive charge because chlorine has a -1 oxidation charge on it. So this has got to be positive, and you know what the charge is on phosphorus? From here. From here. So if chlorine is -1, and there are 3 of them. I know there's 3 of them because of this. These guys come together to be electrostatically neutral. So I know that this is going to come together to be neutral. So what must this plus be? +3. Right? That must be +3. Another way to do it is something called reverse crisscross applesauce. This 3 came from up there. There's a 1 here, but we don't write it, and it came from up there. So this was phosphorus +3 and chlorine -1. The 1 is put down here, and the 3 is put down here. Yeah. And that leads us to what we're doing today, writing ionic formulas. We have our periodic tables out. Yes, the big ones with all the charges on it. With all the charges on it. So some of these you see have multiple charges. Look at nitrogen. Oh my goodness. Some you see only have 1 charge. Oxygen, -2. Pretty much all the time. Fluorine -1, pretty much all the time. Now, in different circumstances, they can have different oxidation states. However, the first one written is the most common. The first one written is the most common. So the most common for sulfur is -2. The most common for selenium is -2. The most common for nitrogen is -3. For phosphorus is -3. But we just had one where phosphorus was +3. Right? We just had one when phosphorus was +3. Now, groups 1 and 2, are there multiple oxidation states? No, there aren't multiple charges. So these guys are pretty dependable. They're pretty dependable. We go over to 13. 13, we got +3, +3, +3, +3. Pretty dependable until we get this thallium. But pretty dependable all the way down. So pretty dependable, completely dependable. And then now you can see kind of what stands out in the transition metals is that they exist with multiple oxidation states, except for a few of them. And the ones that don't have multiple oxidation states, traditionally you are asked to memorize. You should already have zinc and silver kind of pointed out. Remember, it was 3, 2, 1, 3, 2, 1 on your older periodic tables. Is there another transition metal? Those are the ones in D block that only have one oxidation state. Yes.
Ruthenium and rhodium.
Ruthenium and rhodium. Scandium and yttrium. Nice. Zirconium. Nice. What? Yep. Hafnium, tungsten, cadmium. Now, the reason we love this periodic table, actinium, lanthanum. The reason we love this periodic table is because of these. You don't have to memorize these. Unlike without it, you would have to. Without this periodic table, you would have to. Okay, so metals bond with nonmetals. So when you write chemical formulas, like this worksheet is showing you, you have to combine them in such a way that they become electrostatically neutral. Sodium is +1, chlorine is -1. They will come together as we know and love as sodium chloride. Barium is +2 and fluorine is -1. So when they come together to be electrostatically neutral, I need 2 fluorines for every 1 barium. That makes sense to everyone? I need 2 negative charges to neutralize these 2 positive charges. So to write that, I have 1 barium and 2 fluorine. Now, crisscross applesauce indicates no math. If I just put this 2 down there, and I just put this 1 right here, and don't write the 1, I get this. Yes. So potassium and sulfur coming together. What am I going to get? What's the formula? K2S. Lithium and bromine. And LiBr. Silver and iodide. Yep, A Li3. Now, just like in math, we don't want to write Zn2S2. Do you guys know why? We're trying to find the lowest whole number ratio. So we definitely want to simplify to ZNS. So if they match, you just put them together. So don't do that. Simplify. You guys got this? Yeah, yes.
So when we were going over the charges, you were calling them oxidation states.
Mm-hmm.
So why is that? There's not, from what I can tell, there's not oxygen involved. It happens, yeah.
Okay, yeah, so you're gonna learn a type of reaction called a redox reaction. And oxidation is the loss of electrons. Okay, so the metals lose electrons and the nonmetals take them. So oxidation state indicates what's happening with the electrons. So it isn't about oxygen. And I thank you for reminding me. I will call them charges until we get redox, but sometimes I slip. Yes. So Ag2O, is that right? Yeah. Can you guys finish this table? No problem. Are you already done? Awesome. Awesome. So polyatomic ions and parentheses. You often see parentheses being used. You cannot just use them anytime you want. You can only use them when they're needed. Okay. You can only use them when they're needed. So how do you know when they're needed? We're still crisscrossing. Remember, you keep this together as a group. What is this called? CO3 minus 2. What's the name of this one? Carbonate. What's this one? And what's this one? Phosphate and nitrate. Good. So through the same charges, NaCl. Sorry to ask it to you again. Here, how many sodiums do I need for every carbonate? 2. So it's Na, and I need 2 of them for every 1 CO3, right? For every 1 CO3, I need 2 of these, or you crisscrossed applesauce. NaOH, go together, 1 and 1, not a problem. And then here, sulfate is minus 2 also, so I need 2 sodiums for the sulfate to be electrostatically neutral. What about for phosphate?
You need 3.
I need 3. So Na3PO4. And what about for nitrate? Oh, Na3PO4. What about for nitrate? I just need 1, right? So NaNO3. So potassium won't be quite different than that, right? Because it has the same charge. But let's look at calcium. How many chloride ions do I need for calcium?
2.
2. So I'm going to have CaCl2. Now the next ones, calcium is +2, carbonate is -2. So when they match, I can just ignore them, right? So I'm just going to write CaCO3. Now, calcium hydroxide. How many hydroxides do I need for every calcium? 2. So this is where parentheses come in. If I just go CaOH2, that indicates there's 2 hydrogens, 1 oxygen, and 1 calcium. And that's not what we're trying to say. So I need to put parentheses around the OH. And now it's 2 hydrogens and 2 oxygens for every 1 calcium. That's when I need a parenthesis. 2 hydroxides. Calcium sulfate, I can just ignore them because they match. SO4. But calcium phosphate. I need 3 calciums for every 2 phosphates. That makes sense to everyone? 3 calciums for every 2 phosphates. PO4, I need 2 of them. Do I need parentheses? Oh yeah, or else you're going to be adding up 42 oxygens. So, oh. Will I need parentheses in the next one? Yep. Cool. Think you can finish this table?
Yeah.
I'm sorry. What'd you say?
So, yeah.
Okay. So you have, I don't know, why don't you work on this for about 20 minutes? See how much you can get done in 20 minutes. Yes, sir.
So if it was, not a compound, say it was O2, would you use parentheses around, the oxygen?
No,
So you just,
no, that doesn't happen. Okay, so this is ionics. O2 is covalent. Right, so we got to keep that separate. This is metal, non-metal, metal, polyatomic ion. So we are in the ionic realm. Very strong electrostatic forces holding them together. The electrons actually removed, like completely transferred, and then it's opposite attract electrostatic forces that are creating this unit of a salt crystal.
thanks.
No, the whole idea is you don't touch my stuff. The whole idea is we want to keep our
Why don't you put parentheses around calcium, chloride?
because this is a single element. So we do need 2 chlorides. It's not a polyatomic ion.
Oh, sorry.
Right?
Yeah, I was thinking about it. Yeah.
Yeah.
that one.
That is a single element. Yes, sir.
What's the difference between A2 plus and some plus 2, like how it looks like that, is that the same thing?
Nope. Okay. So you can just. You can't change it. Don't change the track. Even remaining. So. We'll get break 3 magnesium, something down to stuff 3. And we'll do some 2. Yeah, I haven't done that for yet. You can't use Apple for this. See this? It's getting 3. Not N-O, not N-O2, not N-O. It's 3. It's all 3 of those. They need completely.
This is. It's like it's like. So like here, it's like the nature. No, just saying, before is like attached. Oh, yeah, it's not. Yeah, I think that is, yeah. Yeah.
Okay. Hopefully you're finished the table. Yes, cool. So we're gonna just cover a little bit of notes to introduce this to you. And that is our first section of nomenclature, and that is how to name ionic compounds. So you can write their formulas correctly. Now you need to say their name correctly. And the first thing, you need to stop that and pay attention here. Don't frown at me. I mean it because I care. First thing, what I want you to do is just envision your periodic table like this. Are we ready? You got to look up here to have your imagination. Envision this as a set of parentheses. Okay. Parentheses are surrounding the transition elements. Does that make sense to you guys right now? Can you remember that? You can remember parentheses, transition elements. Okay, so when naming ionic compounds, not complicated, pretty much every chemical formula for the next couple years for you guys, well, next 3 years probably, will only have two names. Okay, it'll have a first name and a last name. Okay. The first name is the name of the metal directly from the periodic table. Right, name of the metal directly from the periodic table. So metal's name. Then the last name will be the anion or the non-metal. Non-metal that ends in IDE. That ends in IDE. So you're like, how is this hard? How is this hard? Traditionally, NaCl, what do we call it? Sodium chloride. And let's see. What would K2S be? Potassium sulfide. What would BAF be? Barium fluoride. What about LiBr? Bromide. What about aluminum iodide? Nope. ZN is zinc. Zinc sulfide. Silver oxide. Nice, nice, nice. So that works really well, right? And that works if it's a type 1 metal. What? Type 1 metal. What? There are different types. Type 1 metals are the metals that aren't in the parentheses. Right? So traditionally type 1 is like our A group. Our A group metals. But really, type 1 metals have only one charge. Only one charge, meaning sodium is always +1. Meaning lithium is always +1. Meaning beryllium is always +2. Meaning calcium is always +2. Magnesium is always +2. However, and zinc is always +2, and silver is always +1. However, when we get to the ones in the middle here, iron can be +2 or +3, right? Multiple charges. So if it is a type 2 metal, you are going, the first name is the name of the metal. Absolutely. No space between the name of the metal and your first parenthesis. There's no space there. You're going to put a number in here. You're going to use a Roman numeral to represent the metal's charge. So if, for example, it is cobalt +2 that you're using, you would go CO, cobalt, BALT, no space, Roman numeral 2. Cobalt 2 is CO +2. What is CO +3? Cobalt, no space, 1, 2, 3. That's cobalt 3, that stands for CO +3. It is just the first word. This is just like calling Bob, Bobby, Jim, Jimmy. You're just altering the name, but it is the first name. It is not a middle name. Okay. And then the non-metal will end the same way. Non-metal ends in IDE. So if I do COCl2, what is the name of this?
Cobalt 2 fluoride.
Cobalt 2 chloride. How did he know it was 2? Because there are 2 -1 charges for every one of these, so this must be +2. So this would be called cobalt 2 chloride. Cobalt 2 chloride. When a metal has more than one oxidation state, for this having more than one charge, you have to tell the world which one you're using. Are you using copper 1? Are you using copper 2? Are you using copper 3? There is no multiple potassiums. There's no multiple calciums. So you don't have to tell the world that. They know. The world knows. Now, the only other way this can change is if the nonmetal is a polyatomic ion. At which point you will use the polyatomic ion name. Or polyatomic ion name. Well, you had to memorize the name. So, what is the name of this? You got 2 names. You only get 2 names. It's the name of the metal, sodium. And what's the name of the nonmetal? Nitrate. Do not try to split that up. You have to know your polyatomic ions. You have to know that is the anion. Right? There's not going to be 3 parts to the name. If you're writing 3 words, you're doing it wrong. Right? There are no 3 words to names until you're at, level 300 at university. Yes. They can both be lowercase or uppercase depending on, your writing. It's like, yeah, it doesn't really matter. So I got one for you. CU. We got 2 names. You already know the last name. Yeah.
Copper 3 nitrate.
Yes. This is copper 3 nitrate. Copper 3 nitrate. Yes.
So for the one above it, why wouldn't it be sodium 3 nitrate?
Whoa, because okay, great. Nitrate is polyatomic ion, it's all together. Couple reasons. Sodium, group 1, it doesn't vary. It's always +1. Right? So never going to have parentheses for sodium or anything in group 1 or group 2.
Okay.
Right? Second, this 3 stays with the nitrate. Right? This 3 did not come from up here. What came from up here is that you only have 1 nitrate for every 1 sodium, and that makes sense because nitrate is -1 and sodium is +1. You've got to envision those polyatomic ions as kind of their own thing together.
Okay.
They do not break apart. Even in solution, when you put them in water, they stay together as NO3. And the NO3 is surrounded by the hydrogen ends of the water molecule. So even in solution, they don't break apart. They stay together, your polyatomic ions. And you should have a whole bunch of them listed on the back of the periodic table. You're not expected to know them, but you're expected, not that periodic table, the one I gave you. Oh, wow. Any other questions on this? So what I'd like you to do is on your own paper. You are to, on own paper, write names of ionic formula for all compounds on this worksheet. Now, you do not have to repeat it when it's sodium chloride and it's sodium chloride and it's sodium chloride. You don't have to write it 3 times. Yes.
So like all these are the and every single one of these.
Uh-huh.
In the back.
Is that too many?
Maybe just add.
Okay. How about just the bottom table? Is that better?
It's still a lot. I was gonna say like.
The bottom table extends on the
Couple rows bottom, like one of the top.
Okay, so how about, we're gonna say this table, the one on the back,
Yeah.
so that's 6 times 4, 24. And how about this table? Is that a good negotiation? Okay, so is everyone clear on that? You're writing the names for here and for here. So it's 24, 25, 26, 27, 28, 29, 30, 34, 34 names.
Yeah.
34 names. What are you looking for is those Roman numerals, when to use them. I don't know if you want to take a picture of this periodic table so you can zoom into the oxidation states, because you want to know when they, when to, yeah. I cannot, because the scanner doesn't scan it that big. So I need to reduce it, but then when I reduce it on the copier, you can't really read them all. I copy directly from a big one to 11 by 17. It'll do that. But when it only scans 8.5 by 11 front and back. Ooh, I could sacrifice one. Cut it in half and it'd be half and half. Because 11 by 17 is 2. Ooh, I could cut 1 in half and scan it that way.
I'm just gonna write them all out.
Yes, yes, I will do that. No, thank you, because I was like, crap, it didn't do it. I put it through and it didn't do it. Okay.
I have a question.
Uh-huh.
The formula is like F iron oxygen. Do you do
Iron oxide. So
oxide,
what
um,
iron is it?
it's 2, but in the
So-
formula you can use 1. So do you put it?
No. The 2 is not talking about how many are in the formula. It's talking about the charge of the metal.
Oh, okay.
Yeah.
That makes sense.
Yeah, you are not representing the number of atoms in the formula. You're representing the charge on the metal with that Roman numeral.
Oh, okay, that makes sense.
The Roman numeral is here. It's the charge on the metal,
Oh, okay, that makes sense.
right? That Roman numeral is the charge on the metal. Cobalt 2, that's why it's cobalt 2. Right?
Oh, okay.
Cobalt 3, it's cobalt 3. It's the charge on the metal, not how many are in the compound.
That makes sense.
So over here on this one, I'm sure the foreign here. Should it be two and four, should it simplify to
Yeah,
one or two? Yeah.
so you should have a 2 here. Right? Because if you wrote it crisscross applesauce, it would be. You would have 2 or 4, then you would reduce it.
I think it would be.
That's the other thing
What about?
was over here. With this get combined with H2.
So what?
The H2O, yeah. So you don't need when it's a single ion. For instance, these are only 4 polyatomic ions.
Right.
So get rid of those.
So.
That is, that's 4.
So 10.
Chlorine's-
I took yours. Okay, no,
Don't get confused by it. Don't get chlorine. Don't get chlorine but. Yes. Please bring back your periodic tables before you leave. My AP class doesn't get them.
Is our homework to like write the names out?
On paper.
Yeah.
And finish this worksheet.
Okay.
So we also throw these back.
And that's from the note packet from last class. And you got a note packet I handed out. The questions, the quick review questions, they are answered in the note packet, like the first 2 pages of the note packet I handed out 2 classes ago. And periodic table. Okay.